And this is the last talk of today in stage one, and the speaker is Mateusz Dymiński. He's a software engineer with strong technical background in software development, sometimes DevOps. He loves backend, tolerates frontend, and he has over 7 years of experience in Java. But since the beginning of 2014, he has been fascinated by Golang. He is one of the Go Wrots leaders. It's the Golang user group in Wrocław. And during his daily duties, he's building reliable and scalable distributed something. Oh yes, systems. In cloud environment in Nokia. Mateusz has 2 small kids, so he doesn't get much sleep these days. So can I ask you to give an especially energetic welcome to Mateusz Dymiński and his Taking Your Microservices to the Next Level with gRPC. Mateusz Dymiński.
Hello, everyone. As I was presented, today I would like to talk you and tell you about the microservices and how to take them to the next level with gRPC. So the thing and the knowledge which you should get after my presentation is knowing what the gRPC is, and hopefully you will get some extra tips how to solve some problems in the microservices world. So here is the slide about me, but I guess everything was almost presented. As I mentioned, Mateusz Dymiński, software developer at Nokia, 7 years of experience with Java and so on. And as I also, was mentioned, I'm also one of the organizers of Go Wrots, where I would like to highly tell you that it's a great place and be there and just enroll on that. And then there is a GitHub, and this is a place where you can find all the presentation and slides, also all the code which I'm going to present today. And also I have a Twitter where I'm posting something from time to time, and LinkedIn. Okay, so let's go to the presentation, to the main body. So the agenda is that I will tell you what the gRPC is. So the second point here is that I will tell you what are the problems right now in the microservices world. So I describe what exactly what problems might be solved with the gRPC and what is the list, like almost the whole list of the problems in the microservices world. And then we'll go to the demo. I will show you some code samples, and those code samples will be written in the Java and the Go. Most of them are written in the Go. Some of them are in Java. So there will be something which is called by me search engine. So I will show you how more or less Google or other search engines doing the search and how the architecture it might look like. And then we'll go to the summary and the Q&A session. So those are things which should be there. And hopefully the problems will be solved. Otherwise, it's going to be tough, at least for the demo part. Of course, if you have any questions during the presentation, you can just raise a hand and ask. Okay, so that's one of the first things. So gRPC is in fact the RPC on steroids. So this is like a regular RPC framework, but with some improvements, something which is added value to the classic RPC. Let's warm up a bit. How many of you have heard about the gRPC? Well, that's not bad. I guess like 30% of the room. Nice. And how many of you use microservices or building microservices? I guess same hands. That's nice. Hopefully, I will show you some tips, and you will get some extra knowledge and something which you can use in your daily job. Okay. And how many of you use JSON to transfer the data between your microservices? Okay. Still same hands. Okay. also in my presentation, we'll find some comparison between the JSON and the protobuf, because the protobuf is used in the gRPC, and I will also try to explain why the JSON is not the perfect and there are the better way to transfer the data from the model to the bytes. Okay. So what is our gRPC? So the shortest answer is that it's a RPC on steroids. So that's the logo of gRPC. So whenever you will see something like that, it's just a gRPC logo. Okay, so this is a sample diagram how it might look like. So in fact, RPC doesn't have to be used only in the microservices world. It also might be used in client-server communication when the client could be a mobile device like iOS and Android. So if you're using the JSON to transfer the data between the mobile client and the server, the gRPC is also an option to reduce the speed and the CPU consumption, the network consumption, and so on. So in this example, we've got a server. Server is written in C++, and we've got the two clients. One is Android Java client, and another one is Ruby. And RPC is a framework which is created to connect all those machines, the client, the server, and this is the way how in very, very good quality we can have this communication between the different service. But before we go to the gRPC and the exactly definition what it is, we should start from the RPC. So RPC is remote procedure call. So this is just a way how to run some program on the other computer. So we've got two computers, one is the client, one is the server, and we would like to run something on this different machine. So let's assume it says server A, server B, and we would like to run it somewhere. So this is like the gRPC, remote procedure call. So you'd like to run the code there. And it's used in almost all distributed systems. So if you think about the Hadoop, I don't know, Elasticsearch, anything which needs some synchronization between the nodes, RPC is used. Of course, RPC solves some problems. So usually, if we would like to have everything and write everything from scratch, we have to implement something like security, synchronization, data flow handling, and so on and so forth. That's like reinventing the wheel. So the people created RPC just to help you with that. And some examples, probably you might use RPC frameworks, but you don't know that you're using it. So JSON RPC is pretty popular. SOAP, very popular. Apache Thrift and Apache Avro also. Corba, pretty old, but still on the market. And the gRPC, which is new. So wherever we would like to have a communication between the client, the server, and we would like to run some code somewhere, it's RPC. So why the gRPC is better than the RPC? So it's a RPC framework, so it fulfills all the requirements from the previous slide, but it also has some new features, like streaming RPC. So let's assume that we would like to get all the users from the server, we are make a request from the client to the server, and we would like to get all the users. So usually we have methods, let's say REST, and we would like to get 100 of them, and then another 100, and so on, until we get all of them. In the RPC, we could have something like streaming RPC, where we have a method getUsers, and it will return a stream, and it will return one by one all the users. So in that way, we can be more reactive. We can react on every single user which comes to the client and show it to the end user. Let's assume that we are building some mobile client. And in that way, we have a way to also establish the communication in both ways. So on the same stream, we can send something and we can also receive something. So this is also good for chats or somewhere where we would like to have like a duplex communication in both ways. It's also multi-language. So if you would like to use it as a communication layer in your microservices world, and you get some team which is really good in C++ and another which is in Java or Go, then you could just use it because the implementation are in three first languages, so Java, Go, and C. Those first three languages have their own implementation, and the rest of the languages are using the C implementation, in fact. And I guess that's most of the most popular languages nowadays. So the way how we are describing the service and the way how we are telling what would be the contract between the servers. Let's assume that we have the server and the client, and we would like to have a method get users. So get users should be somewhere written. Somewhere should be the contract. What would be this method? What would be the request? What would be the response? What the fields will be there, and so on and so forth. So the ideal it's that, and protocol buffers is the one way to describe the service and describe the methods, describe the objects which are transferred on the wire, and another one is flat buffers. Flat buffers is something new. It was introduced, I guess, in September. And this is a very efficient way of transferring the data because it's invented by the game industry, I guess. And then we've got the transport. So the gRPC is using the HTTP under the hood. As probably you know, HTTP2 has a less number of connections. So we can have one single connections and run multiple number of requests during this one pipe. So if we've got a web browser and we've got HTTP2, then in the old HTTP 1.1, usually it was a 6 simultaneous connections to get something. Like when we are opening the web page, we are doing 6 simultaneous connections to get the content, like CSS, JS files, and so on and so forth. In HTTP, it's usually 1. The servers might run more clients on the same hardware because the network and the CPU is better utilized. And of course the security is there, so there's SSL, TLS, everything is configured, so we can just put it and we don't have to worry about that. And it's one of the most important things is that it's open sourced. So if you have if you've got some issue or some problem, you can just create a ticket in the GitHub. Someone will at least fix it if it's bug, or you can fix it by yourself. And you can also see how the people from all around the world created gRPC. But generally, our gRPC was invented by the Google and Square, mostly from the people from Google, but also there was some communication with the Square. Okay, so main usage scenarios. So you might think when we should use that. So the first thing is when you are efficiently connecting polyglot services in microservices style architecture. So as I mentioned, if you've got a communication, you've got a microservices. One microservice is responsible for user, another one for, let's say, for invoices. Of course, the communication between and write it in a gRPC is just perfect, and it was created to do that. Connecting mobile devices, so not only microservices, but also, as I mentioned, if you've got iOS client, Android clients, and mobile devices, use gRPC. And generating efficient client libraries. It's also popular to build the SDK based on the gRPC, and that's what Google is doing right now. Some of their SDKs for the Google Clouds are written into the gRPC as a communication layer. So Bigtable, also in Java and Go. So those drivers, if you would like to put something in the Bigtable, you're using the SDK from Google, and it's using a gRPC under the hood. Low latency, high scalable distributed system. Perfect example here is a Kubernetes, and Kubernetes is based on the etcd. So etcd is the distributed key value, and it's really the heart of the Kubernetes, and the communication between all the nodes and the state and everything is based on that. So this is written also in the gRPC as a communication. Okay, so who's using that? Of course, Google, because they've invented that. There are examples with Google Cloud. Probably they're using that internally. But no proof. At least I don't have many proofs that they're using that internally. Netflix has a Netflix Ribbon. It's also based on the RPC Square. Those are the people who are also with cooperation with Google created the RPC. Cisco, and then Cockroach. I don't know if you can see that, but Cockroach DB This is a database, like a distributed SQL database with transactions. So it's written in Go, and they're using gRPC to communication and to synchronization between the nodes. Docker, not the Docker itself, but communication between the in the tools which are created by people from Docker are also based on the gRPC and CoreOS, and their most important product, which is etcd nowadays, I guess, is written and based on the gRPC. Okay, so some tools, as I mentioned, Docker, so previously was a companies, right now we've got concrete tools, so CockroachDB, etcd, Google Cloud Bigtable, so if you'd like to have a SDK and you'd like to put something there, you're using gRPC in fact. And YouTube Witness, it's this is a way how Google is scaling the MySQL in the YouTube. So, so in fact, it's a MySQL, but it's distributed, and they are storing everything in MySQL. But in front of that, those all MySQLs is a witness, and the communication is on the based on the gRPC. Those were Go examples. Here are the Java. So again, Google Cloud Engine pops up. So it's a queue, and Google Speech, Netflix Ribbon, and TensorFlow, which is a deep learning platform. And they're also using it's mostly in C++ written, but there's also something in Java, and it's written and they're using gRPC. Okay, so so now let's talk about the problems in the microservices world. So let's talk what should be there and what knowledge and what things we have to have in mind to build something really good quality. So usually it looks like okay. So usually it looks like this. So we've got a huge poo, and we would like to divide it into small pieces, but they are still poos. I mean, if you are not able to create a good quality monolith, probably you won't be able to create a microservices with good quality. So that's why it usually looks like that. And unfortunately, it's really common that someone who has a big monolith and it's bad quality, it uses then approach to microservice, and it's still bad quality. But the list of the things which you have to in mind to create a proper microservice is that long. This is a list which was created by one of the Reddit user, JCombinator, and Hacker News, and it's really cool because it also shows how smart and how aware of many things you should be to build really good microservices. And then gRPC helps with some of them. Those first 5 of them are distributed, are connected with the communication. So if you've got a communication problems, or you would like to create some nice API, then this is something which is here at the beginning of this list. And let's go step by step with those problems. Distributed tracing. So if you've got 4 servers, microservices, let's assume, we've got a server A, B, C, and D, and if you've got one request which comes to server A, and then it's passed to the server B and C and D, and you've got some problems, let's assume that between the C and D, and you would like to know exactly what's wrong and which communication between which services is broken, or at least it's timeouting, or there is something wrong. If you have no distributed tracing, like Zipkin, like OpenTrace, like all those fancy things from the Google Cloud, with a Stackdriver, I guess, where you can see exactly the diagram with all the calls. So it's based on some request ID, which is established at the first server, and then it's passed to all of them with the same request, which is passed down, and then you've got a really nice diagram. So if you're using the gRPC, you could just use some tooling, which it's a way just of configuration, and then you've got these diagrams on place. So it's really nice to use gRPC to have a distributed tracing. Then build, expose, and maintain good APIs and contracts. So if you've got the microservices, one of the most important thing is to have deploys which are pretty independent. Let's assume that you're using JSON and you would like to add a new field to the service A, like to the model with a service A. And then if you have a deploy, the deploy should be independent. So if you've got two components and you have to deploy them in the same time, simultaneously, because otherwise you will get a bug and the server B has no idea how to decode the new field which was introduced in the model. This is not a microservices, it's just a monolith with some communication between those. But it's really important to have API versioning. Even if you're the same person who is building the both services, you have to have API versioning, and doing that with gRPC is much easier because it's protobufs, because in fact you are describing what fields are added in the message. Let's assume that we are passing the message from the server A to server B, and the rule is that you can only add new fields at the end. You cannot change them. So it's not like in the JSON that you can remove something or you can add something. It's that you can only add something at the end. And then in that way, easily you can have some backward compatibility. And the contract, in fact, you can have one single place when all your protobuf files are stored, and then without any problems, you can pull this for, let's say, let's assume that it's a repository, pull that and build your microservices based on this one single place. So there is no problem with synchronization between the models, because service B and service A, they've got their own model somewhere. Okay, so backward-forward compatibility. This is also what I've mentioned, and then it's a provide quality of service. So it's QoS. Let's assume that we have a distributed service, and we would like to have a deadline. And let's assume that we would like to get the response in 100 milliseconds, but in fact we are making the request to the server B, and the server B is running another 3 requests to the server B, C, D, and E, and then we've got a problem. How to cancel all those requests if we have a quality of service set to 100 milliseconds? So if we promise to someone that we can return the value in 100 milliseconds, that's the problem. Of course, we can have some timer, and then if the response won't come, then we are returning the value. But we are still have all those requests made, and it's still consuming the CPU, the network, in all those services. In the gRPC, you can have this cancellation. You can send a request, another request that, hey guys, I'm not looking for those results anymore, so I'm up. And of course, and provide request propagation cancellation, same story. This is also connected with this distributed tracing, because in that way we have a way to propagate all those requests in our microservice, and then we can cancel them, and then we can also trace them. Okay, so let's go with a demo. Let's build some search engine. So let's assume that we've got a client. Usually it would be the web browser client. So if we have a Google, then we type some Wrocław and we are looking for the result. And in this example, we've got a client, which would be the CLI, because it should be simple. And then we've got a front end, which gets this request from the client, and it make another request to both backends, and then gets the result. But the fastest response wins the race. So we are provide the response to the end client as fast as the fastest of the backends returns the value. So, and we say that to the second backend, which is still consuming some time and waiting for the result, we say, okay, guy, we are not looking for any more for this result. So. So this technology or a pattern is called fan out. So we've got the one request in the front end, and we just split that into multiple backends, and then we are waiting only for the fastest response, and then we are sending that back to the client. Okay, so this is a timeline. So in our example, we've got a client, front end, and two backends. So here we've got a client, we are making some query goes to front end in the same time is doing two queries, one to backend 2, one to backend 1. They are thinking about the result here and here, and here we've got a reply from the backend one. It goes to front end, and the front end replies to the client, but in the same time, it cancels the backend two. So it tells the backend two guy, I'm not looking for the result anymore. Just cancel this request. Okay, so let's go to the demo. So I've got all those components. I will run them. So this is a backend number. Its index equals to 0. So this is the first one. Then we've got another backend index 1. Those two, the backends are written in a Go. Then we've got a frontend. Okay, so let's run that. And then we've got a client. And the client is written in a Java. Just to show that it's not always that everything should be written in the same language, because this is a polyglot microservices where we've got components in different languages and they can talk to each other. Okay, so let's run that. We can have a, okay, so now we are calling this backend, and we get a result here. So here we've got a result for hello code dive. So this is a way how we are going to search. So it's a synchronous mode. We are calling method search, but those are the params which are not important. And here is a query. So this is the only thing which is important. We are looking for only for the hello code dive, and we are getting the result from backend one. Let's call it one more time. Okay, come on. Another backend one, unfortunately. I will show you that it's sometimes backend one, sometimes backend 0. Depends on the... Okay, so now we've got backend 0 here. Okay, so it means that sometimes we got the response from backend 1, and sometimes we got the response from the backend 0. So we are getting the response as fast as possible and cancel the another one. And in gRPC, there's also, in Go, the implementation, there's also example how we can debug the connections and the requests and responses. So let's go here. So this is a front end, and those are the backends. Let's start from the backends. If we have this console, this is like HTTP server, which shows out the back information. We have to run that debug mode manually, but it's really nice. And we can have some really nice and fancy information here. So let's start from the backend. So as a backend, I understand this. So here we are right now in the backend one. And here we can see that we've got the 3 requests, and so here is the information that we received those 3, and here is the normal summary, and we can expand that. And here we've got some fancy information. So we can see that we got RPC from some address. We have no deadline. I will introduce deadline later on. We received a query with some value, and then we've got information that we are sleeping for some time. There is a OK that something is just calculated, and then we are sending title result for la 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 from backend 0. Here is also from backend 0, and here is the third request here that we got a result from backend 0. No, and in those 2 previous requests, we got a backend request response from the backend 1. So it means that here we didn't return the value to the end, to the front end, but we got information that we are cancelled. So the front end sends the information, oh, come on, I'm not looking for the result anymore because of this. And it was asynchronous. We can use also asynchronous client. I will show you the code later on, how it's implemented, how it's done. But let's go also with this with this deadline. So we can use a deadline search. And here we've got information that we cannot return the value because deadline was exceeded. So let's go here and have a look and see what's happening here. Okay, we've got no request. Okay, and this is the second backend. So here are also the 3 requests, and deadline is too short right now. So so let's go to the front end and see what's there also before we go to the deadline. Okay, so at the front end level, so let's go for a moment here. So we are right now here. So in the front end, we've got the two types of events. So we received something and we sent something. So we received the request from the client and we sent the request to the backends. So so we can go here, and as we can see, we've got the 3 requests here to the backend 1, 3 requests here to the backend 2, and we've got the 6 sent requests to the backends, and 3 was to backend 0 and to the backend 1, and 3 was to the backend 2. And here is the expanded view, and here we've got the information that hello code dive, and we've got information from which backend we are getting the information, and that we are canceling some of them. Depends on which was faster. Yeah, and okay, let's get back to here for a moment. Okay, so we got this this demo with this event logs, front and back end. Okay, okay. So let's go to the code. Hopefully you can see that. Maybe not the comments, but the code. So this is like the heart and the most important thing, which describes all the behavior of both of all the components in this service. So here we've got at the top we've got a couple of metadata, I would say. So there is a package. Package is a package which is used in Go, but there are also some options, and those options are connected with the Java. So if you would like to create the codes based on this protobuf in Java, we have to add some information like a Java package, Java multiple files, if it should be only in one file, only multiple files, and what would be the class name outer, and so on and so forth. Here's the syntax, is protocol buffers 3, and there's a package in the Go. And then we've got a service, I've called that Google or a search engine, wherever. And then we've got, here's the most important thing. So we've got the method search. So now we can search for the result. And if we've got the client and the server, then we've got a different implementations, and in fact, if we've got such method, then we have the implementations based on this metadata. So the protobuf is generating the code in Java in a Go. I will show you in a moment how we can do that, but it's generating the code for the server with this method, and it's generating the code for the client with this method, and it accepts the request. And the request here, we've got explanation what's there. So there is only string query. And then we've got the result, and the result has 3 things like title, URL, and snippet. And this is how we can describe the services, and then we know how to generate the code. Let's go here, how we can generate the code in Go. So in Go, we need the protobuf. So we have to go to the GitHub of protobufs and then build that and install that on our operating system. Then we've got the Golang protoserve wrapper. This is just a way how we can, based on this protobuf in implementation in C++, generate the code in a Go. Then we've got a way how to generate everything and all the code in Go. So we've got a proto-C search proto, then we are having some output with this plugin, and it's gRPC, and it's a Golang search. So this is the place where all the code is generated. And then we've got Java. So for Java, we are looking for the Gradle or a Maven. So those are okay, we are again here. Okay, so there's a Gradle, a Maven, which is needed if we are doing some tooling all around the Java, and they've got some plugins. So there is a plugin for Gradle, plugin for Maven, and then in that way there is a configuration in a POM file or in the build.gradle file, and then we are telling him where exactly is this proto file and where the code should be generated. And then we've got the code in Go. So this is only a piece of the code. So in fact, it's like a 300 lines of generated code. But what is most important? So here's the interface, which is a server. Here's the interface, which is a client. and there is a request and the result struct. It also has some also annotations like JSON. So what would be the value in the JSON after the marshalling? Same story with the protobuf, and here is also the result and all the metadata like annotations. And the most important steps are here. So there's an interface which should be implemented to run the code as a client, and interface which with the method which should be implemented to run the code. So there's a context. So context is like a bucket for metadata which is passed with all the requests to the next server if we are doing a request in a Go, and there is a request itself, and we got the result or error if something goes wrong. Same story with the client. We've got the context, we've got the request, and we've got some extra options where we can set some security deadline and so on and so forth. We are getting the result and the error. Okay, so now we've got the request. In Go, it's 300 lines. In Java, it's much worse. So there's around like 4,000 lines generated or something like that. Only the client has like 1.5K of lines of generated code. But the nice thing is that they're also generating the builder pattern and all that nice stuff. And also the most important thing is that it also generates the 3 types of clients. So if you got a client and the server, the client has a API like a blocking API, asynchronous API, and also some streaming API if we are set the streaming. So okay, so let's go to source code of every single component here. So CLI client it's a Java. So we got a blocking client. It implements the search client, and it has a constructor. Constructor gets only the host and the port, just to know where to establish the channel, in fact, because the channel is in fact the communication pipe between the servers in Java. So on this channel, we are able to create the blocking stub. Blocking stub is just a type of the client. So we've got the blocking stub, we've got the non-blocking or asynchronous stub, and that's how we are telling what client would be used if we are in a Java world. So it should be pretty straightforward. There's a channel and there are the service. So the service implements this method like a search, and the channel is in fact the real connection. And here is a method search. So if we've got the method search, so this is like an implementation of that. So we have a query. We are building the request. So it's a builder. As I mentioned, the builder is already automatically generated from this protobuf file. We have a setter set query. Then we are building this object. So we've got a request. And we, with this Google blocking stub, we are using that, and we are passing this request to the search method. If it's success, then we are logging that it's okay. If not, we are logging that. Get unchecked, this is a try monad. So if someone used Vavr in Java or try monad, that's a way how to get rid of the try catch. And then get unchecked just gets the result, whatever, if it's a checked exception or not. And just to simplify this code and make it more nicer. Here is the same with asynchronous code. So we've got, again, same story. We are building the request. And here, the difference is that we are getting the classic result, but we have a listenable feature. And the generic here is that we are getting the result if we call the get method. So with this result feature, we are calling get, and we are telling him, we can call a get which will wait indefinitely until we get a timeout, but here I call the get and I'm telling him give me the result in 100 milliseconds, otherwise he will throw an exception. So that's the Java code. So let's go to the backend because it's easier. This is Go. So here, first line for flag pass. This is just to get the index which I pass in the CLI. Run seed, I'm using the random there, so I have to seed the random just to make it random. And then this is a really important line. So here I'm running the HTTP debug server. So the fact which I was showing to you in the web browser is run on this port here, and it's because I've run that in the new Go routine. It should be familiar for you if you were on the William Kennedy, who is in the audience, talk. So Go routine is just for the Java or C++ developers is like a new light thread. So it's run in the new thread, and it serves all those files and establishes this debug mode. And then we've got the listen. So this is like we are listening on some, and we are established the connection, the TCP connection. If something went wrong, then we are returning fatal, which ends the application. And then we have a new RPC new server, and we have to register search engine server. So this is a method which is generated automatically, and then we are passing here the G. So it's a server, and we are passing new server. Server is this is a type which implements the method search. So before this func main, there is also the server type, which implements this interface. I will show you later on the implementation, and then we just serve that on this particular TCP connection. So here is an implementation. So here is a server. It means that type server implements the search method. Here is exactly same method which is in this interface, which was automatically generated by the Go code, this wrapper. And then we are sleeping for random duration. We are logging that, and then we have a select. Select is a really nice thing where we can listen from different channels. So let's assume that we've got two different channels of the data, the pipes where the data is sending to our thread, and then if the duration here, so the time which we are sleeping is longer than some time, we have an event which goes here, and then we are returning the result that we got a result. If the front end got the response from the other backends before this sleep lasts, then we have an extra event from the context done channel that someone else was faster than we, and we should just return the error. And here is a front end. Front end is the most complicated because we are the server and the client. So we are the server for the CLI client, and we are a client for the backends. Here we are just making the channel, so a special type in the Go which contains all the results, and then we have it's as long as the number of the backends, in our examples 2, and then we are range over those backends, and we run in different Go routines. So in fact in this new light thread, we are passing here the backend, and this backend is calling the search method with the same context, because we got this context here, so we are passing that, and we are sending those requests to those two backends, because it's run twice, because we are ranging over the backend. So here are the two backends, so we are doing that twice, and then and if we got some result, then we are sending result to this channel. So here we are doing the channel for the results. Here we are sending the results here. And here is the magic. So the channels are, if we are try to get something from the channel, it will wait for the result. So here we are doing something in a new Go routine, and this Go routine which executes this function goes here and waits until anything goes to the channel C. This is not a perfect solution, because we should also clean up the second thing which might go to this channel, and so on and so forth. So, but for the demo, it's a simplified. And then we are returning the first result and first error if it comes. Here is the type of the result. So we are only waiting for the first, and we are returning that as fast as possible, and we don't care about the second, which also might go from this channel. And here is here's the main method. So the way how we are doing that is also, we are also starting the debug mode with this extra HTTP server. We are also have a listener on the main port. So this is a port which starts the server. for the client, CLI client. And here we have a same story, but here we are creating the clients for the backends. And we have to, in fact, create two of them because we have to create a client for each backend. So frontend has a server for the CLI client, and it also contains two clients for the backend backend 1 and backend 2. So we are creating them in the loop. And here we are doing same for the server. So this is exactly as it was in the backend, but here we are creating the client, and here is the same story. So the client has to implement this method. Okay, so what's better than a demo? That's the question, and then the answer is another demo. So let's go right now to the streaming API. So the way what we'll show is a streaming search engine. So we would like to debug ActiveStream, and we will also see how the request cancellation is done, but also it was presented before, but we'll see how the request cancellation in the context of streams is working. So here is an example. Here is the timeline, how it will be looking. So we've got the client, same story, front end, same story. So a query goes to backend 1, backend 2, but right now we are not having only one response, but we are starting sending all the responses to the front end here. So we are returning the responses for all the time until until the client cancels those requests, and then we just get the cancel in a front end, and then we are propagating that to the backend 1 and backend 2. So until before we go to the implementation, we can run that. So it's exactly the same story. So we'll assume that we would like to have some code dive, I don't know, dive 4, and here is not a search but a watch method. And it's not a deadline, but it's a set stream. Okay. And now we are getting the results. Sometimes from backend 0, sometimes from backend 1, with some random delays between the responses. So let's go to the code. Let's go to the web browser and see how it's done. So right now, what's changed is here. So in the front end right now, here are the requests and the response. But here we've got the two active connections which are sending the requests, and we have one active connections which is getting the request. So let's go to the active connections here. So here we've got the request which we are getting from the CLI client, and so let's see what's there. We can refresh that, and we see that at the beginning we got some query, so we received that, and after that we are sending the responses. And here is that 155 events is discarded, so for simplification they are not shown here, but for all the time, if we refresh that, we have a new values. So we are getting all the results which are passed to the end client. And also we've got two connections here, connection to the backend 1 and to the backend 2. And here also we sent a query, and then we received results. Same story here. And this is how we can also debug all the connections, and on the active connections we can see what's going on the streaming, if we of course add this extra go routine which starts the HTTP server in the debug mode. Let's go also to the backends. So here and here. So here we can see that we've got one request which lasts like 95 seconds. Of course we can refresh that. Come on. And here it's also 95 seconds. So it means that it's still open. So we are sleeping for some time and we are returning, and the context was cancelled. Okay, so this is how it looks if we are doing that. It was killed because after some 100 seconds I just killed that. So there is also something in the code which just ends that at the end, but we can of course run that one more time. Okay, come on. Okay, now we can one active as well in the backend. We can, of course, expand that. We are seeing that we got some requests, and then we are sleeping for some random time and returning the values. Same story here, one active, expanded, received hello code.4, and then we are returning the responses. Okay, so let's get back to the code and let's see how it's implemented. So right now we've got a new method here. So now we've got a watch method, and the whole magic which stands for the streaming is the stream keyword. So if we put the stream here, instead of getting the response, we are getting the channel of the response in Go, or we are getting some listener in a Java just to get all the results, and then we can just have some handler which gets all the results. Okay, so let's go and let's see how it's implemented. So the only change in the constructor is that instead of new blocking API, new blocking stub, we've got a new streaming stub, and the difference here is that we have a stream observer, and this stream observer returns the results, but it also has to implement all those methods like on next, on error, on complete. If someone is familiar with the RX Java, it's the same story. So there's also observer. So it's something common to that approach. So we have 3 type of events which might come from this active stream. So the next value, the error, and the complete when someone cancels that and ends everything, and then we get information. Okay, it's ended. Everything was sent. And here is a way how we are waiting for until the stream is ended. So we are using the countdown latch here, and we are just waiting until it gets some 100 seconds, and that's why it ends after the 100 seconds. Okay, so let's go to the Go implementation. In Go implementation, we've got the watch method instead of a search method. So implementation is that we have a stream context. So we are just assign it to this variable. But later on, we are doing almost same thing, but in a for loop. So now it's infinite loop, which for all the time sends the responses. But if the stream gets the information that the stream was cancelled, then we are returning. So the only way is if something goes wrong with the connection, and we are return the error via this channel context done. And otherwise, we are just sending everything here. So we have a stream send, and the stream, in fact, is just this stream of data, and we are sending every duration this result there. Otherwise, if someone cancelled that, we are going there. So that's a small change. And here in the front end, it's a bit more complicated, because we have to pass. We got 2 open channels from the backends, and we've got an open channel to the client, and we have to combine the results from those 2 channels and pass them to the end channel, which is where we are server for the client. So here is we are using the wait group here, and also the stream context as well, and also we are making the channel for the results. Same story. We did that before, but right now we've got a new watch backend method. We'll go there in a minute. But what we are doing here, we are adding the value for the wait group. So and at the end, here we are doing information that we are done, and here is a place where we are waiting until this wait group is finished, and if it's finished, then we are closing the channel. So the trick here is that if we've got the channel and the information goes to this channel, we can range over that channel like we are ranging over the slice in a Go. But we have to be sure that somewhere and in some time will someone close this channel. So here we've got information that if both these new Go routines do their job, they close this, they call the done on this wait group. So if both of them are done, then we can close this channel, and we are informed this loop that okay, there will be no more responses in this channel, and we are just end that story. And here we are sent. Okay, so and go right now. Let's go to this watch backend. So in watch backend, we've got every single backend. We are calling the watch method on this backend, which returns the stream, which is a pipe, like the channel, so the pipe with those results. And then in select, we are returning the values. So this arrow means that come on, get me as fast as something appears in this channel, get the result. Same story with context done. So if something goes wrong, if we got the error, we'll get this here. If everything is okay, then we are getting the results from each backend here. And then here we are just receive the stream in infinite loop, and if and we are just passing this to the channel which is here. So here is the channel which we got from the method watch, and now we are putting this channel. So this channel is shared over two invocation of this method. So once this method is invoked by the new Go routine, which is looking for the results from the backend 1, and another one is from backend 2. So then we are sending all the results to this channel, and then it's combined in this previous method and sent to the end client. It's not that easy if you are not familiar with the Go, but it's really worth to have a look at that and run it in a home, and then you will be definitely more convinced that it's really nice and it makes a good job. Okay, so it was demo part. So now let's go to the end of the presentation. So let's talk about the ecosystem. So gRPC was involved, like it was presented almost 2 years ago. So right now there is some ecosystem all around the gRPC. So there are some tools on the market which are created by the community. So there is a gRPC gateway. This is something which is written in a Go, and the reality is that you cannot right now use the Go from the browser, from the JavaScript client in the browser, because of some of the limitations of the HTTP2 headers. And they're going to solve them in the newest browsers, but right now you can't run the client in the pure JavaScript in the web browser. So if you would like to have a client which is using some REST endpoint to get the data, it's a tool which generates, based on this protobuf file, automatically the whole REST endpoints. So you can just type some generate codes based on this protobuf, and then the whole REST server is created, and then you can use that from, let's say, Angular or React or whatever the JavaScript client is. There is also the Prometheus. So if you have Prometheus as your monitoring, then you can just establish and use this gRPC Prometheus. Then you've got everything sent to the Prometheus with some few lines of configurations. Really nice thing. In the Go, there is also a package which is called middleware. So there is lots of really nice middlewares which doing some nice job, like putting something in the context, or establish some security, or passing some extra values via the context, so on and so forth. So interceptors, authentication, logging, really nice stuff if you are using Go. And then gRPC open tracing. This is same story like a Zipkin, because if you would like to trace and get all the details of invocations of your microservices, then you can use the gRPC open tracing. And at the end is also polyglot, is gRPC command line. So if you've got the microservices written in a Go, you can generate the codes, and in a polyglot you can just use it as a debug just to get some information from the server. So that's also nice. And okay, so hopefully I showed that gRPC might remove some little pulls from your architectures. So if you've got this like 20 of little poos in your architecture with microservices. Hopefully 6 of them might be removed with the gRPC. So let's treat gRPC as just button in the flush and then just remove them by using this. So that's really nice. Just to sum up what I've shown, so use gRPC when efficiently connecting polyglot services in microservice star architecture. So if you've got if you have to establish some communication and choose some technology to connect different microservices, use gRPC. Really nice, really fast, much faster than JSON, built-in API versioning, one place where all the metadata is, really nice stuff. Connecting mobile devices, so not only microservices, also server and the mobile client. Use gRPC then. Generating efficient client libraries. If you forgot some API and you would like to create the SDK for some developers, which might be based on your service, use gRPC. And use gRPC when creating low latency, highly scalable distributed systems. It's also really worth to take that technology. It's as I mentioned, fast, good, invented by people at Google. So really nice and smart guys are created that. And why? Because gRPC is the answer to most of the microservices problems. There should be also a dot, because it's not for the most, but most connected with the communication. So if you've got the problems with communication, with established API, the contract, and so on and so forth, then use gRPC. Thank you.
Woohoo! It's time for woohooing. Thank you very much. Mateusz Dymiński.